Excellent. Cool. Give people a moment to kind of get into the live chat. Was it this class that we had the conversation about the Rubik's Cube? It was? Okay, cool. I brought it in and yesterday or no today, and I'm like, who did I bring it in for? And just for you guys, and nothing but you guys. Yeah. I will talk about the Rubik's Cube very briefly in a little bit, but this is a one that I've used in the past. I haven't been to a competition in like 3 years. So I haven't actually been practicing ever. That's why I try not to keep them in the classroom, because if I keep them in the classroom, they tend to be a bit of a distraction for me, and I tend to just like methodically solve them over and over again. But that's besides the point. So I'll talk about that very briefly. Let me just tell you what we're going to be doing today. We're going to be digging deeper into simplifying rational functions and simplifying rational expressions, I should say, as we go deeper into this chapter. My initial goal is to go over to have you guys take a short quizzes. It is a 10-question quizzes, a practice quizzes. Will not count against you, but I want to see where we're at based on, well, what we did before break, and most importantly, what we just did on Monday, kind of having you take it cold without my help at the beginning. I would like to review some of the questions from that quizzes, and then I would like to take things a little bit step farther into this world of simplifying rational functions. You'll see how that kind of goes in a little bit. In the meantime, I will talk very briefly about this Rubik's Cube, but I'm going to ask that while I do so, please make sure that you have your Chromebooks out and open, because the first thing that I do want to do is that quizzes. And obviously you need the Chromebooks out and open in order to get that thing done. For those of you that are in the chat, if you would be so kind to leave a comment, that would be wonderful. There we go. You can leave a comment in the chat, and I can check the attendance later. That'd be fantastic. So, the Rubik's Cube. Now, I'm not going to spend a million years on this thing, but this is what they call actually a stickerless Rubik's Cube. I know people jokingly say in the past, they're like, oh, just peel off the stickers. Oh my gosh, it's so frustrating to hear people say something like that. Even if they did or they didn't, just kind of peeling off the stickers is just not something that I like. What's up? What?
I was walking in the hallway, and on my shoes I have a bunch of people's signatures.
Okay.
And I was walking in the hallway, and the teacher said, "Oh my God, I love your shoes." And I said, "Oh my God, thank you so much." And then he said, "Are there some signatures?" And I said, "Of course." And I said, "Would you like to sign them?" And he signed my shoes. His name's Mr. Putman?
I don't know.
I don't know either.
All right. Well, I'm talking Rubik's Cubes, you know. Now, obviously, I'm not going to solve it with my feet for you today. That would be disgusting. Absolutely disgusting. Feet was an official event, actually, for the World Cube Association, which is the governing body of all this thing. It's really, messed up. I was very involved with the World Cube Association up until about 3 years ago. But then after we had our second child, I'm like, yeah, I don't really have time for this anymore when my daughter was born in 2018. So would you agree that this is sufficiently scrambled? All right, cool. No. Nah. You know how many different ways you can scramble a Rubik's Cube? 43 quintillion. 43 quintillion. It is a lot. You could start counting, and the universe would end before you're done. Yeah.
1, 2, 3. I'm just kidding.
Yeah.
That's so silly.
Yeah. So the other thing you got to know about Rubik's Cubes is that it has been mathematically proven. It has been mathematically proven that any Rubik's Cube can be solved in 20 or less moves. So the people who say, "No, let me scramble it more," see, it just fell and broke. No, it didn't break. People who say, like, let me scramble it more. No, it's pretty much sufficiently scrambled. So stop trying to think you understand how to do Rubik's Cubes. So I'll just do this like impressively right here for you guys. Again, I haven't solved one of these in a while. But it is like getting right back on a bike. I'm doing it for the camera as well, so the people in the camera can see it. I used to be able to average like 30 seconds for one-handed. Not so much anymore, simply because I am way out of practice and I don't remember most of the algorithms. But that is besides the point. It's not that hard to learn. It's done. See?
Missed the mark.
Yeah.
I can only solve like one side.
Yeah.
I can't even solve one side.
Yeah, I can barely solve one side.
Yeah.
They have like every color on one side except for one.
Oh.
And usually it's like an awkward like middle piece too.
Well, the middle pieces don't move.
No, not the middle piece as in like the middle piece. Like the middle piece as in like one of these.
Oh, one of the edges. I got you. So,
Middle edge.
like that. Oh.
You just
Yeah. Oh.
Algorithms.
what?
Depending on where they're supposed to go, you can solve them. I have a tutorial online on my personal YouTube channel. There's a half an hour tutorial giving a beginner's method as to how to solve the Rubik's Cube. It is a beginner's method. Like I said, it's about 30 minutes, but there are timestamps in the description, which are very helpful because those timestamps in the description, you can obviously watch like 10 minutes of it and then like, okay, let me practice this. And then you come back the next day and you won't have to rewatch or find anything. So. Two hands. I'm not going to do that now today or right now. Maybe I'll do it at the end of class. But when I was in, actually in the middle of it, like practicing going to competitions, I could average like 14, 15 seconds. Yeah. World record average is about 6 seconds. Okay. That's average, mind you. World record single, I believe now is just around 4 seconds, maybe 3. It's been done. I've seen it done. Anyway. I don't know where this conversation just went. I'm going to pretend like it wasn't something terribly inappropriate. Yeah. But we all know it was terribly inappropriate.
What are we doing?
Huh?
What are we doing?
A quizzes to start.
Okay, thank you.
Yeah, sorry. I had explained that when you were out of the room. So, let me get this quizzes up and running.
Is it okay if I put that slide through below so we can just like start my computer?
That's sufficient.
Okay, thank you.
You'd be surprised, like the people who like are the best in the world at the Rubik's Cube competitions. You might think like, oh, just these nerds and blah, 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 blah. But like these guys make thousands and thousands and thousands of dollars per competition. Not even talking per year. I'm talking per competition. They have sponsorships. 332. There we go. They get to travel all over the world to go to, obviously not during COVID, of course, but they get to travel all over the world for national competitions, world competitions, continental competitions through the companies that have made the equipment that they use. Like one that I use over here, I bought from a company called The Cubicle. The Cubicle is an independently owned business stationed, I believe, in Rochester, not Rochester, New York. It's just outside of New York City. It's not Rochester, though, but it's outside of New York City, and it was made by a couple of kids who they, were huge Rubik's Cube speed cubing competitors, and they wanted a better product. So they went to school and they learned how to make a better product through biochemical engineering and other forms of engineering and business acumen. They're able to create a very successful business. Yeah. Okay, if you say so. Wait, is it the single world record or the average world record? What's the kid's name now? Wow.
Oh, it's always the fat people.
It's not.
I'm kidding, that was a joke.
No, dude, that is Max Park. Okay, first of all, Max Park is not just some quote unquote fat Asian kid. First of all, he's from California. He's American. Okay, he has autism.
His nationality is Asian.
Regardless, he has autism, and he is one of the most popular speed cubers on the planet.
Well, doesn't having autism make you smarter?
Not necessarily. I think
Yeah,
that's a
but-
huge misconception.
But don't you have like not necessarily smarter per se, but don't you have like better understanding of certain things or like?
It depends. It really depends. It depends on the severity of your autism. It depends on where on the spectrum that you fall. It depends on a lot of different things. A lot. This kid, Max Park, interesting. I met him when he was 15 in the 2017 Nationals.
Well, of course you have a story.
Of course. Kid won the 2017 Nationals at 15 years old. He had only been like really speed cubing for like 2 years, which is insane. But then the very next weekend, he went to Paris and won world championships.
What's the difference between Max Park and just doing his best?
Say it again.
What's the difference between Max Park and just solving?
Max Park is on another level. He's on another level like Felix Zemdegs, which you don't know the name Felix Zemdegs. He's from Australia. I need more people logged into this. Apparently, I have 8 people
He's not
in.
fat. What are you talking about?
I have 8 people in the live chat. I have 7 people here, yet I only have 7 people logged in right here. Those people in the live stream need to be getting into that quizzes because I'm going to be starting it soon. If you know anyone who claims that they can solve it, like, oh, I have a cousin who can solve it in like 5 seconds. I'm pretty sure you don't, first of all. Second of all, if there is somebody in the Northeast that can solve it in about 5 seconds, I guarantee you I know them. Just saying.
Oh my God, you did it in 3.846 seconds. That's crazy.
Anyway, let's get this thing started. I would strongly suggest a scratch piece of paper. For these problems. Again, we're going into them cold. I am going to be reviewing the most troublesome problems, but let's see what we can do. Remember, factoring is key. Greatest common factor, Tucker method, if need be. Let's see what happens. For those of you that have not logged into this game yet, you need to make sure that you do. The code will still be live. Oh, and just a side note, if there's a picture that is too small on the screen, I believe if you click the picture, it will enlarge itself. You'll be able to see what's going on.
Are you good at chess?
I'm decent.
That means
Not like, competition work good, but I know how to handle myself.
Period.
so. Like, you think in a random matchup you would win? Just against anyone.
It depends on the caliber. Like if I went to like the chess club at the school, I'm fairly certain I would get wrecked. If it was just like you pick a random kid out of the cafeteria, yeah, it's probably wrecked up. I doubt it.
Southern is the cafeteria open, they make them put up the things.
That's so stupid. Oh, sorry, Mr. Monkey.
I'm not certain on the details. We actually have a faculty meeting today.
I
But,
can tell you about the school, full time again.
well, we know when they're going to full time again on the 26th, but we just don't know the exact details as to how it's actually going to transform. Maybe they'll do the cafeteria shifts. Maybe they'll have kids eat in the classrooms again. I have no clue.
Wait, are we having, we get one day off?
Yes, the 19th you do.
Oh, sweet.
Mr. Monkey, you're doing really bad.
I'm sorry. It is just practice.
You're also doing
If you click on it, it'll work. give you guys another minute or so to wrap this up. If you're not done, that's okay. But I would like to begin reviewing some of these problems. Okay. Click, click. Do. Okay, so what I want to do is, like I said, I want to review a couple of these problems, not all of them, but a few, just to kind of make sure we're on the same page with them. You will not need the Chromebook, but I will ask that you do have those notebooks out and open in order to copy down said problems and to build upon some of the skills that we learned last class. So what I'm going to do is I'm going to switch this over to questions, sort by accuracy, and I am going to start at the bottom down here. And I am also going to have this open as well for my notes. Zoom out. There we go. Let's see what we got here. Today is the 14th, and I am calling this Simplifying Rationals Practice. That is what I'm going to be calling this thing, Simplifying Rationals Practice. I am going to be taking a step farther into this realm of simplifying rationals involving the operations that we've learned, but let's just see what we got going on here. The first problem I would like to go over, looks about half of you got this one wrong. I'm going to have it written down on my paper. I'm going to flip the camera back. X squared minus 4 over x squared plus 8x plus 12. Good place to start. That's exactly the problem I want to start with. Now, when it comes to simplifying these things, just as a reminder of what we've done in the past, a lot of people would immediately want to try and cancel out those x squareds. And I'm telling you that you cannot cancel out those x squareds. You are not allowed to cancel out those x squareds. The reason comes down to the operation that is separating the term from the rest of the problem. Now, I can show you some concrete examples in a moment. I'll write them on the board. But let me just say this. If addition or subtraction is separating the term from the rest of the problem, then you cannot just cancel them out by dividing.
See, I remember that. I just don't know why. Which, I'm sorry, I know that's really...
No, it's definitely not. Let's say... instead of variables, I use numbers. Instead of that 2, it could be an x, right? So you could say, well, instead of this 2 over 2, it could be x over x. I'm saying, no, you cannot. You cannot, absolutely cannot just cancel out those x's just because it's x over x. There's addition separating the x's from other parts of the problem. If I replace those x's with 2's. Exactly. The actual simplified version of this should be the fraction 5 over 7. Should be 5 over 7 because you do the parentheses first. But if you cancel out the 2's just because you're like, they look like they cancel, you get the wrong answer. Yeah. No, that's no problem. That's what I'm saying. I wanted to repeat the statement that I made in the previous class period, but then I wanted to show you that concrete example up here because it's like, yeah, 2 over 2. But the 2 is being separated by addition, so you can't do it. So instead, what we talked about on Monday was the fact that we needed to factor. We needed to factor. Now I'm going to go through a shortened version of the Tucker method of factoring. Greatest common factor is always your first step. However, the greatest common factor of both the top and the bottom of this fraction are a 1, so we can't do anything with it. So I move on to the next step. Now, shortened version, can you give me 2 numbers that multiply to -4, but also add up to 0? Can you give me 2 numbers that multiply to -4? Yeah, and also add up to 0, right? X minus 2, X plus 2. The only reason why we're allowed to do it that quickly is because there is a 1 in front of the x squared. If this were not a 1, then we would have to do something different. Looking at the bottom of the fraction, I can do the same thing. Can you give me 2 numbers that multiply to 12 but also add up to 8? Multiply to 12, add up to 8. Give me any 2 numbers that multiply to 12. 2 and 6. Yeah, you can say 3 and 4, but oops, sorry, 3 and 4 add up to 7. Yeah, it's got to be 2 and 6 in this case. X plus 2. Oh, she said it in the chat. X plus 6. Sometimes, for those of you that are in the chat, sometimes the words that I say, there's a little bit of a delay. Like if I were to actually open up the YouTube video right now, there would be like at least a 2 or 3 second delay between what I say and what shows up on the video. So my apologies. But now, and that is what you were saying. Oh, I froze, like my heart. There we go, unfrozen. Now, like you said, like, you couldn't cancel out those x squareds before. You couldn't cancel out those 2's before. But this x plus 2 is a single term in its own little set of parentheses that is only being separated by multiplication and division. Same thing with this x plus 2. So they would cancel each other out. As a result, the simplified form of this problem would look like this. You cannot simplify it any farther. Mr. Markey, what about the -2 and the 6? Sorry, I can't touch the -2 and the 6 because addition, subtraction separate them from other parts of the problem. It can only be simplified under multiplication or division. It can only cancel out in that fashion. Let's take a look at another one. Going back to the quizzes. Well, we did a problem like that. And we did a problem like that. That's a decent one, but oh, there's a good one. This one's going to take a little bit more time. This one's going to take a little bit more time. Let me copy this one down, and then I'll show you what I'm working on. This example, 5x squared plus 11x plus 6 over 5x squared plus 14x plus 9. Flip. There it is. There's the example right there. Now, you cannot cancel out the 5x squareds for the same reason that we couldn't cancel out the x squareds before. But for this problem, I am going to have to factor both the top and bottom. I'm going to use the Tucker method. If you have other alternative ways of factoring these things, then by all means, use those ways as long as you can show me the work. You have to be able to show me the work. You can't just use some method that you found on a website that some website did for you. That doesn't prove anything to me. I can typically figure out when you're using those websites. I choose not to say much. But this first part, let's take a look at the numerator. 5x squared plus 11x plus 6. I got to take a look at that numerator, and I got to try and factor that thing. 1, there's no GCF I can take out. 2, I multiply A times C. 3, I have to find magic numbers. Now, this is just a coincidence. This is purely a coincidence. But can you tell me two numbers that multiply to 30 and add up to 11? I say purely a coincidence because no one's going to say it. Yeah. She said it in the chat. It's 5 and 6. Yay. It's 5 and 6. It's just a coincidence that happens. It could have been anything, really. It all depended on that 11. If that weren't an 11, if that 11 were a different number, then we would need different magic numbers. Ah, it fell in my heart. But now, again, reminding you of the T-chart. Magic numbers in the bottom. I put a 5x and a 5x in the top. I have to simplify that garbage down if it can simplify. And 5 over 5 does indeed simplify to 1 over 1. Thus, my brand new numerator is x plus 1, 5x plus 6. That's my brand new numerator. And I'm going to put that over here as my brand new numerator. X plus 1, 5x plus 6. I have to do the same thing with the denominator. 5x squared plus 14x plus 9. I'm going to move a little bit more swiftly through the rest of this problem because it's pretty much the same thing. 1, take out a GCF if you can. That's a 1. 2, multiply A times C. 3, find those two magic numbers that multiply to A times C and add up to B. In this case, it's 14. In this case, holy crap, coincidence, it's just 5 and 9 again. 5 and 9 being the outside numbers. That does not always happen. T-chart, 5 and 9, 5x and 5x. Simplify that garbage down. It becomes x plus 1, 5x plus 9. Again, this method of factoring we've been doing pretty much since September. If you've used alternate methods of factoring, that's fine, again, as long as you know how to back it up. What was that method that somebody mentioned on Monday? The X thing?
The X thing, yeah.
Yeah.
That's where you put the bottom one as what you need to multiply, and the top one is what you need to add.
That's the thing. Somebody tried to explain to me like all the steps with using that X method, and I'm like,
If I'm being completely honest, I don't remember how to do it. I tried to do it on the first time, and just include things. So now I'm trying to do that one.
I gotcha.
But learning two methods is not something.
That yeah. If I were to teach you guys like, hey, here's 3 or 4 different factoring methods, and if I were to continue teaching those 3 or 4 different factoring methods, you guys would be like, no thanks.
Well, that's what happened.
Oh, okay.
I was taught two, and it was like, okay, you can pick this one or this one.
Mm-hmm.
So I just picked one randomly. Because
Sure.
What students do. And I don't really remember it because I just don't remember it.
I understand. It's been a couple years. But in the end, the x plus 1s cancel, and you're left with this. Nothing else can simplify from that fraction in the top right. Nothing else. The 5x's cannot cancel. The 6 and the 9 cannot reduce. The only way that something would cancel from the top to the bottom is if they matched exactly. Hold on, let me repeat that statement because I have an example I want to show you that's not on the quizzes. The only way that something is going to cancel from the top to the bottom is if they match exactly. I have an example I need you to write down. One that's not on the quizzes. Check this out.
You said you need us to write down?
Need you to write down. Absolutely 1,000,000,000% need you to write down. Look at that.
I'm sorry, what is that method called that you use?
The Tucker method. The Tucker method of factoring quadratics. I had briefly reintroduced you guys to it before break, I believe, but then that's been a couple weeks. Number one, number two, then we took the benchmark, and then obviously I had a couple weeks off. So I tried to slowly but surely reintroduce the steps. There's always 5 steps to it: GCF, A times C, magic numbers, T-chart / simplify, and then writing out the factors. Look at this example. This example, looking at it right now, nothing cancels. I put this example up here for a very specific reason. I have a lot of people who would just look at this example. They would look at this example, and you know what they would tell me the answer is? They would just say, 1. No, it's not. You can't do it that way. But this can be simplified. First of all, look at the denominator. This 6, I need you to recognize the fact that that is a positive 6. That is a positive 6. This x is technically a negative x. Technically. Let me rewrite the problem. All I did was switch their positions. I switched their positions in the bottom of the fraction. Now, I'm going to do a step, and I need you to tell me what the heck I just did. I'm going to do one more step, and then I need you to tell me what the heck I just did to go from the middle step to the third step. What in the heck did I just do? Can we all agree that I've done nothing to the top of the fraction? Yeah, I've done absolutely nothing to the top of the fraction. Top of the fraction, don't worry about it for now. Leave it as is.
I don't know how or why you did it, but you reversed it.
Okay, well, from step 1 to step 2, I reversed it, right? So I literally, it's kind of like the commutative property where it's like, A plus B is the same as B plus A.
Saying how at the first 2 you had a positive 6, now you have a negative 6.
Well, can we all agree it's still positive 6 here and here?
Correct.
Okay, and it's still negative x here and here?
Correct.
Cool. Now here, I took out a negative 1 as the greatest common factor. When you take out a greatest common factor, you are to divide both terms by that factor. I divided both of these terms by negative 1. If you divide this by negative 1, I can't say it. If you divide that by negative 1, that becomes positive x. And if you divide that by negative 1, it becomes negative 6. And I left that negative 1 sitting out front as a greatest common factor. Well, to an extent, what would happen if I took that negative 1 and distributed it?
Like to the top one, you're saying?
No, just to the bottom. If I took that negative 1 and actually distributed it back into those parentheses.
It would be the same thing as it was previously.
Exactly. I would just be going backwards, right? The reason why I did this is because the numerator now matches part of the denominator by multiplication division. What happens when two things cancel each other out? What are you left with? Or what happens when you divide something by itself? What do you end up with? 10 divided by 10, a billion divided by a billion, x divided by x. What do you get? Yeah, you get 1. This ends up being 1 over -1, or just -1. It's a weird problem. This problem is designed to trip you up and make you fall on your face. That's what this problem is designed to do. It is designed to trip you up and fall on your face, because in the beginning it looks very like, oh, that's very straightforward. There's not a lot of bells and whistles to it. But ultimately, getting that final correct answer, a lot of people stumble, and you need to be careful. You absolutely need to be careful. Okay. I want to show you one more thing to kind of finish up this class period for the last 15 minutes. And it is this. I need a new title. This title is adding / subtracting rationals. Question. What grade were you in when you first learned how to add and subtract fractions?
Definitely not 3rd.
But it was later elementary school?
Correct.
Okay.
Honestly, I think it was in 5th grade. I remember Miss Flynn teaching me, and I didn't know what was going on in the next grade.
I gotcha. What is the one major rule about adding and subtracting fractions? When are you allowed to add and subtract fractions?
When they have the, I don't know.
What were you going to say?
I was going to say we have a common denominator.
Yes.
Oh, actually?
Yeah.
Oh my God.
If fractions have a common denominator, then you are allowed to add them together. So, for example, what if I had 2 over x plus 3 over x? Do they have a common denominator? Yes, they do. What would be the simplified answer?
5 over x.
Yes. And that is the other rule that you have to know about adding and subtracting fractions. Once you've confirmed that they have a common denominator, you add the numerators and you leave the denominator the same. That's what you've been taught, right? Everything's perfect. No change to that rule whatsoever. None. Give me a fraction. Any old fraction. 2/3. Give me another fraction with a different denominator.
6 over 9.
Give me one that's already simplified.
2. Oh. Sorry. Oh, sorry, that was a funny. 1/2.
1/2. You cannot add them together right now. You cannot add them together as is. What must I do? Which in this case, I have a denominator of 3 and I have a denominator of 2. What is the common denominator? Again, this is like late elementary. I didn't teach any of you this.
I was going to say 6, bro.
It is.
Bro, I'm on fire today.
All right. But it is 6, yes. 3 and 2 have nothing in common by themselves, but you can force both of them to be a 6. How do you force the 3 to be a 6? Multiply times 2. But the rule that you learned way back in the day, and I'm putting this in a different color so you can see it a little bit better. The rule back in the day was that if you multiplied by 2 on the bottom, you also had to multiply by 2 on the top. That was the rule that you learned back in the day. You had to alter the way that the fraction looked in order to force common denominators. This rule that you learned back in, let's say, 5th grade, it's been a minute, is going to play a major role in this chapter.
So you do have to do that.
Say again?
So you absolutely have to do that. That rule stays the same.
Yes. For this one, you said the common denominator was 6, so I'm going to multiply by 3 over 3. Technically, what am I multiplying by? This whole fraction, what am I multiplying by? Yeah, I'm technically multiplying by 1. I'm not changing the value of the number. I'm just changing the way it looks. Because ultimately, I get 2 fractions. I get the fraction 4 over 6 plus
Oh my God, I have a perfect statement.
3 over 6.
Just like how we're all human, but we look different. We're just all different fractions.
Should I clap?
No. Okay, continue.
Okay, they said no, so.
I'm sorry, guys.
Oh, goodness. All right, back to this. Ultimately, you get the fraction 7 over 6. Again, this is something you guys did back in, I'm assuming 5th grade, let's say, give or take. Maybe 6th grade, maybe 4th grade. I don't know. I did not teach you this stuff. But this is the stuff that you learned back in the day. And Madison, you said the statement before, so all the rules that we learned back in the day, they're still true. They're still valid. Yes, they all are. Now check this junk out.
No, you're gonna make me confusing.
Maybe.
No, I hate when you give me a glimmer of hope.
Here's the next problem that I want to try. Now, I didn't make it crazy. I tried to make it as simple as possible, but still involving the variables that I want to deal with. You cannot just make this a 7 over x plus 1. If you do, it's wrong. The same rules apply. If you are adding fractions together, they have to have the same denominator. Again, 5th grade rule. Y'all went to like different elementary schools, right? Or most of you did?
We adjust and we're homies.
All right. I'm saying because with the redistricting, now every kid's gonna have like the same school for like a grade level. Yeah. It's interesting. I went through the Barnegat school system. I think I've told you guys this before. I kind of wish they did have the redistricting because when I went to Brackman, it's like a whole new world of people. I don't know. But then when I went to Southern in 9th grade, another whole ocean of people.
Oh, it's so weird. Now, like, they all know.
Yeah. I think that's better, personally.
I remember coming to middle school and being like, wow, bro, there's a bunch of new boys. Little 6th grade Maddie with like her hormones, she was like, wow, boys. Come on, Mr. Murphy. I know you guys went through the same thing.
Saying, wow, boys.
Maybe. I don't judge.
All right. Back to this. What's the denominator on this 5?
1.
They do not have the same denominator. But I can force them to be the same denominator by doing the following step. I can multiply the top and bottom of this fraction, 5 over 1. I can multiply the top and bottom of this fraction by x plus 1 over x plus 1. Now, technically, x plus 1 over x plus 1 would cancel each other out, but I'm forcing it into the problem in order to force a common denominator on that second fraction. Now, mind you, I'm not doing anything to the first fraction. Sometimes you may have to do something to the first fraction. Sometimes. Not all the time. Because now this first fraction has a denominator of x plus 1. I didn't do anything. But now look at this second fraction. If I were to multiply the denominator on the second fraction 1 times x plus 1, I would get x plus 1. Do they now have the same denominator? They do. But I just have to take care of one extra little thing. Up here, I am going to have to simplify this numerator. Look how I just did that. I'm going to have to simplify this numerator by distributing that 5. Then I have to do this magical thing that you learned back in, I think you learned it back in pre-algebra. You all took pre-algebra in like middle school? Yeah, I think you learned this magical phrase, combine like terms. I think that's pre-algebra. Okay, just making sure. This is what has to happen. This is what has to happen over the course of this chapter. We are going to have to simplify various things like this. If you are multiplying, dividing, you're going to have to factor and see if things can't cancel out. If you are adding or subtracting, you are going to have to find common denominators and force those common denominators into existence so that you can combine fractions by adding or subtracting. It's very weird. It's very strange. But that is what this thing does. I don't want to do that example today. I'll do a different example today. I'll do one more example, and this will wrap up today. Check this junk out. 1 over x squared plus 2x plus 1 plus another fraction 1 over x plus 1. It may seem complicated, but this problem is actually very, very, very straightforward. I see a quadratic here. What the heck have we been doing with quadratics for the past several class periods? What have I had to reteach you about quadratics? What is this concept known as breaking quadratics apart into pieces? What do we call that? It's that magical word that starts with an F and ends with an actoring. We did it! It was insane. I can't believe it. It's wonderful. You must factor. Watch what happens when I factor this problem. Look what happens when I factor this problem. No, not necessarily. Watch this. Do you notice that the first fraction, after I factored it, has multiple x plus 1s, right? This one over here does not have the same denominator. What is it missing? The second fraction does not have the same denominator. An additional x plus 1. So check this out. Check this out. If it's missing an additional x plus 1, I can do something like this. I can multiply the top and bottom of that second fraction in order to force a common denominator. I can force a common denominator. And ultimately, once I force that common denominator, then I can add these two fractions together. It really is insane. I'm going to wrap it up here. We are going to pick up with more of this on Friday. Make sure you have that answer written down. I'll leave it up on the board right here for a few more minutes. But that bell is going to ring in approximately 3 seconds. So, we'll see you then.
That was really good, this Marcy. You said 3 seconds, it was like 3.
It's like I know numbers or something. If you haven't left a comment in the chat, please make sure that you do so. I will leave this open for a few extra moments just in case.
Have a good day.
Thank you too. See you. Okay. I left it open for that time. No one commented.
Mr. Murphy, I have a question.
Yes.
Is the speaker